it's Wednesday. We are already halfway through the basics, right? What is the principles? And we will of course talk about applications a little bit later, but you need to know the concepts first, right? You need to know the words. Can you hear me at the back? Is okay? So we will continue with what we taught last time, which is basically diamagnetism and paramagnetism. But before I do that, I think we need to tell you some of the evaluation, part of the evaluation. So one good way to evaluate is that you make a presentation. So I've given a list of topics, and you can choose one of them, or you can choose some other topic related to magnetism. I think those are a lot of topics, but anyway, if you have some particular interest, for example, which is not listed, for example, you have topological insulators, suppose, and you want to talk about that. I didn't list it. You're welcome to do. Of course, use your common sense. It has to be related to this topic or this subject. And on Monday morning, we can some feedback. So on Monday morning, we can take that up in more. What we will do is 15 minutes you make presentation. It's quite short. Short is always tough actually. You think short is good. Means you have to condense a lot of information into a short period of time. I've given some examples of other people's presentations. Some are longer than 15 minutes, but you can judge what you want to do. But I've in your course material you have some examples, right? So have you had a look at it? I hope. If you have not, please do so. Or you can contact Chintamani and he will pass on that information if you have not received for some reason. Some example presentations, but you can also discuss with me, right? After any of the talks you can come and discuss. So basically on Monday morning, I would like you make a 15-minute presentation which is quite short, but that is actually tough, as you will find. That means you have to condense all this information into a short period of time. And 5 minutes will be the question and answer. Okay, so that part we won't be recording this, obviously, for the Gian, for the upload. So you don't have to feel nervous or something. And then we will also have a term paper. So you have to work quite hard during the weekend. Of course, part of the weekend we are also teaching, so it will be quite intensive. So you can start today itself to do the assessment. So we will have term paper, and I will give you the format. And you can choose application if you like. You can choose theory also if you like. So, for example, you can have choose some research paper or some article you find interesting. It can be, for example, about magnetic levitation, right? You find it interesting, or you find superconductivity and magnetism interaction interesting, or you find biomedical applications interesting, right? Then you prepare a write-up on it. Okay, so what kind of write-up is required? So the write-up, basically you have to be at a postgraduate level. So it cannot be very elementary, correct? It has to be somewhat sophisticated. And essentially I look for 2 or 3 things. One is you provide introduction to the subject, explaining its significance. Since this is you're not doing research, you have to explain why you find this topic interesting to you. It could be some reason you could have why, or it could be a worldwide significance. Anyhow, whatever topic you choose, you should show why you have chosen that topic. And Then you describe that topic, what it is. You can take some figures, you can take what you like from some source, but there are two things. One is, you must acknowledge that source if it is not your own drawing or your own words. Secondly, if it is some words, right, you cannot just take the whole sentence or the whole paragraph, right? Even though you have referenced that particular sentence, it doesn't mean you can just reproduce that sentence as it is. This is a common misunderstanding, that since you have referenced it, you feel, I'm not trying to do something which is not correct. But in fact, it is also still not okay. So you have to reword it or rephrase it, yeah, in addition to referencing it. So follow these principles, but feel free to take from wherever you want. Yeah. Your whole world is open to you if you can take from some reference or some and reference things, have a list of references. But more importantly, I want to see what you feel are the challenges and future directions. See, in every field there are some problems. So for example, in medicine, if you see, you may read about many advances being made in medical field, no doubt, every day you see. But also, if you really go to a hospital, you see the reality is very different. So there is a gap between the promise of some particular topic and the reality of that topic. So why is there a gap, and how to fill that gap? Correct? So that is something which is personal to you, how you choose to do it, and that will be the toughest part. Because naturally, other people have also thought of the same thing, and they are trying to think, hey, how can I fulfill this gap? Correct? So it's not easy, but it's very intellectually important. So we can discuss how many pages and so on, we can discuss later, but I just want to tell you what you should do. It's not, in my view, it's not difficult. I think all of you have made presentations before, and it's not competitive. So you don't have to worry what other person does. You don't have to feel there is some competition. So I think you take this. We can discuss more details later. So let's move on with the subject itself. I think you guys have understood what I was stating. What were we looking for? Diamagnet anyway, not so important, right? It's very weak. Paramagnetism, we understood how magnetism in a paramagnet varies with field and temperature. Correct? And we established this can be described by the Langevin function. So that is a very good, we have already climbed one sort of peak. Now we have to go to the next peak. Because this was classical, and you know that we have to now go to quantum. So that is where we stopped last time, so let's move on. I'm just going through this just to visually you can remember what we did. There are so many things to cover, so I don't want to redo what we already talked. Anybody saw that frog? You have access to internet? Oh, you don't have access to internet. Okay, maybe you can see the levitation if you get access to the internet somewhere. If you need access to the internet, otherwise it may be, how can we provide them? Is there a way?
You have to give the map.
Okay, can you, because you can't, term paper and all that, you would like to browse, please contact the volunteer and to get access. Is it okay? So this is the Langevin function, correct? So we have m by m naught. This is a well-known relationship, which is the fruit of all the labor that we have put in. Okay, so now we move on to the quantum side. So in the quantum theory of paramagnetism, energy is discretized, that is the Planck postulate. So E is equal to h nu. So in the case of what we are interested in, the potential energy of each atomic moment, which I put as minus mu dot h, right? That means mu h cos theta. That's the angle. Dot product means cos theta. But here the important thing is that theta cannot take any value. In the classical case, theta can be any value. So theta can be any value here. But in the quantum case, theta is discretized. So there are several possibilities, right? So it can be that theta can assume only these two values, or it can be that theta assume this values. So you have different possibilities in the case of quantum theory, correct? I think you know this already. So you recall from the last time that the magnetic moment in the classical case is E by 2 mn, and there's the p orbit, and mu spin is E by m p spin, right? So this we already derived, we showed in the earlier case. So in general, we say that in general form for this, mu is equal to g e by 2m times p. So for the orbital case, g is equal to 1. That means 1 times e by 2 mn times p, correct? For spin, g is equal to 2. That means 2 cancels with 2 and you get e by m times p. So this g is called spectroscopic splitting factor, and this is the magnetic moment. The angular momentum, which is p, is given by h by 2 pi. So now here you can see the quantization, because this is Planck's constant. Okay, so now we have already quantized our angular momentum, and therefore we have quantized the atomic magnetic moment. Because if this is quantized, actually this is also quantized. Okay. So if you have, this is for one electron, suppose you had just one electron, but if you have many electrons, then all those orbits of the electrons, they combine. They combine and you get a resulting orbital angular momentum of the atom, of the electrons of the atom, to be more precise, and that is given a quantum number called L. So now you come to the quantum theory. So in the orbital, quantum angular momentum is quantized by a factor called L. The spin momentum is also quantized using a quantum number S, S for spin. And then this orbital quantum number L and this orbital number S, these can be related to a total angular momentum, which is given by quantum number is J. So the spin and the orbital contributions combine to give total angular momentum, which is described by J. And you find basically that the effective magnetic moment of an atom is given by G into square root of J into J plus 1 multiplied by the Bohr magneton. So now here you can see that the atomic magnetic moment is quantized because these are discrete numbers. Okay, so now we move further. We, instead of saying which theta is allowed, we can say this also, but instead what we do is we talk about the values, potential values of the atomic moment in the direction of the field. So this is the mu effective, and it is aligned with the field, you get mu h. Okay, so in that case, this square root of j into j plus 1, you can call it some m, right? So finally you come out that the magnetic moment in the direction of this field is g times mj times mu b. So j can be, take values j, j minus 1, j minus 2, or minus j minus 2, minus j minus 1, minus j. So j is a positive integer or it's a half integer. Okay. So if you have j equal to 2, so then you can have 2, 1, 0, minus 1, minus 2. So if you look, you can have 5 possibilities. So j equal to 2, there are 5 possibilities. 1, 2, 3, 4, 5. So that is the case for j equal to 2. J can also need not be only integer, it can be half integer. So j can be half. So you can see here, if j is equal to half, then you will have plus half minus half, 2 values, right? So it is here. So you can get j equal to half, j equal to 2. So this is the way we understand the quantum theory of paramagnetism. So no, I think it's is it on? Okay, seems to be okay. It's again, the volume has gone down. We have to increase it again. There's some, it's not stable. Hello, yeah, that's better. Little bit less, yeah, right. So now you have the maximum value is obviously this value, j, because that's the maximum. So mu h is equal to g into j into mu b. So what is g? G itself is some, as I told you, it's a combination of j, s and l. There's a spin component, there's a orbital component. Okay. In some cases, the orbital component is very small, almost 0. In many important cases, L is equal to 0. And so J is equal to S, because J only depends on L and S. If L is not there, then J will be equal to S. Then you will get G equal to 2 and J equal to half, which is what I showed you. So this is a useful and common case. So Mj will be plus half and minus half. Of course, as I told you, how to go to the classical case is all values of j are allowed, which means j is equal to infinity. That means all angles are allowed. Suppose, on the other hand, opposite case, there is no spin. Suppose S is 0. Then j is equal to L and g equal to 1. Okay, so if you have fully spin, then j is equal to 1, and if you have fully, if there is, if there is no orbital contribution, g is equal to 2, and there is, so you will get either between factor of 1 and 2. In reality, the g factor will lie between 1 and 2. So as I said, often it is the case that the orbital contribution is negligible. Okay, so now you can derive the Brillouin, it's a spelling mistake here. You can derive the Brillouin function using the same logic, and in the classic case, the magnetic moment is mu cosine theta. It can assume any value. The potential energy is mu h cos theta, but in the quantum case, it is given by this number. Okay. So according to Boltzmann statistics, the probability of an atom having energy is given by, you know, this e to the power e minus e to the power ep by kt. So you substitute this into this and you will get the probability is g into m mu b h by kt. So now if you go through some derivation, I don't want to go through all the derivation, but you can see it. What you get is something that looks like the Langevin function, because you see this is like the Langevin function, but it is not exactly the Langevin function. And also it contains the parameter which gives you the field and the temperature dependence. So you see the same game is being played. Don't be confused by so many L, S and all these. These are all just ways, right? Eventually you see you are expressing M in terms of H and T, and you have succeeded in doing that. This time you are using some quantum numbers, that's all. So, you know, don't lose sight of the main goal. The main goal is to express M as a function of H and T. And so following the same logic as we did for the classical case, we can arrive at this relationship. Okay. So M by M0 is given by this function, which we now call the Brillouin function. As I told you, for classical case, J is infinity. Okay, so you can show that this term will just be 1, this term will just become 1, and this term will become minus 1 by a prime. You can just go through the mathematics. Because of lack of time, I am not doing that, but essentially if you substitute very large value of J, you can show that it comes to the Langevin function, which it should, correct? So the other possibility which is common is J is equal to half. That means either up or down, and in that case the Brillouin function reduces to tan hyperbolic a prime. So this is tan hyperbolic a prime, and you can express for these two cases what should be the magnetic moment. So again, going through some mathematics which I will skip, you can read at your convenience. We get M by M0 is equal to tan hyperbolic a prime. Okay. Now we can move little bit further and look at the susceptibility in the quantum limit. So if you look at the susceptibility in the quantum limit, you can see it sort of looks like what we derived yesterday for the classical limit, correct? It looks somewhat similar. Only thing is, here you have mu effective, whereas earlier you had mu, right? That's the only. Okay, so this is mu. Mu effective is the component of mu h in the direction of the applied field. Okay. So these are the quantum expressions for the susceptibility. Again, in the Curie constant can be expressed even in the quantum case, and we can derive the expression for the susceptibility. Okay. So now, how does this compare with experiment? Correct? We can derive all we like till the end of time, but we need to see how it compares with the experiment. So if you take a paramagnetic substance, okay, I think I cannot read it very well. Can we, so let's fix that. Slightly exchanged. Yeah, beautiful, okay. It's perfect. So here you have the magnetic moment of potassium chromium alum, and these are the experimental values. Okay. Now in the classical case, so what are we plotting? We are plotting magnetic moment as a function of h by t. Why h by t? I told you h by t is the guy we always use as for a prime, right? A or a prime has that ratio of h by t. Okay. So if you see, the classical case is not bad, it's not bad, but it goes higher than the experimental value at higher h. You agree? So here it's not bad, but from here onwards it becomes not so good. Then you can try different values of j. If you put j equal to s equal to 3 by 2, g equal to 2, you get very good agreement between theory and experiment. So that means really the quantum theory can express very much better, but the classical theory also is not bad for under certain conditions. So it depends on the application you have in mind. So now this is the mathematics, right? So I just want to take one step back. Now what you have learnt is the classical theory of paramagnetism. You've also learnt quantum theory of paramagnetism. The details are available in any book. You can work out if you like, but you should see the logic of it. What do we want to derive? We want to derive magnetization as a function of field and temperature. So that is, we have to relate this m to this a or a prime, right? That we do in terms of the magnetic moments. Okay, so now what are paramagnetic substances? And so for example, salts of transition metals, salts and oxides of rare earths, rare earth elements can be paramagnetic. In metals, you have different contributions because the electrons are free. Electrons are free to move. You know that electrons can move freely in a metal. So There are different types of effects in a metal. The conduction electrons show diamagnetism. The core electrons show diamagnetism. But you can also get a paramagnetism of the conduction electrons. Okay? So that is called Pauli paramagnetism or weak spin paramagnetism. So you have both diamagnetic effect and you have a paramagnetic effect. Why do you have this? Diamagnetism you have because the electrons are free to move. When you apply the field, they oppose the field. In the case of the conduction electrons have a spin magnetic moment. Each electron has a spin, and that spin of one Bohr magneton gives rise to paramagnetic contribution. Okay, so now, and somebody asked this question also yesterday, if you have a system like copper nickel, if you have an alloy of copper and nickel is ferromagnetic. Copper is not ferromagnetic. So as you add copper to nickel, the Curie temperature keeps falling. I think we discussed this also, so we had asked about this. The Curie temperature keeps falling until there is no ferromagnetism. So beyond this composition, you get paramagnetic behavior. And very close to pure copper, it becomes diamagnetic. Okay? So you can get this effect, diamagnetic effect, paramagnetic effect, ferromagnetic effect, all in the same alloy system, depending upon the composition. So once you fix the composition, its behavior is fixed. Okay? So you can change the properties by changing the alloy composition. Now, what happens if you have a material like copper, which is not ferromagnetic, and then you add small amount of magnetic elements to it, like iron. So in that case, you will get a contribution from the paramagnetic contribution. You will get a contribution from the ferromagnetic, and you add up these two contributions to get the total contribution. So if you have an alloy, so far mostly we are talking about pure elements, but if you have an alloy, then you sum up the contributions of the two different components, so to speak. Okay. Let me see if I can show you a video for this. So what we are trying to, 1 minute, let me go back and show you. It's not going to the end. Okay, I will re-upload this and I will re-download this and give it to you. Okay, it's not moving forward. Okay. So with this we have come to the end of the diamagnetic and paramagnetic section. Next we will cover ferromagnetism, but before I do that, I would just like to go through the tutorial questions for this part of the course, right? It has to do with diamagnetism, and we will cover the tutorials in another lecture. So of course, this is the main show. Before that is all the trailer, because this is what normally people think of as magnetism. Okay. Those who came a bit late, who are taking the course for credit, just contact those who came in the morning, and you can find out what is the assessment. Okay. So ferromagnetism, I'm going to explain. I'm going to continue, as I said, I'm not going to keep on introducing new concepts in every lecture. I'm going to keep that same concept so that you only have to learn a few concepts and how to apply it. So same molecular field which I told you about earlier, I will use in this, and same that A which is ratio of H by T also I will use in this, and I will show you how to understand this. So ferromagnetic materials, as you know, are materials which are, example is iron, cobalt, nickel. So among these three, iron is the highest, you can see, which is lucky because iron is the cheapest also among these three. So iron is the cheapest and it has a high saturation magnetization. And you recall from earlier lecture that as you apply the field, the material, the domains move in such a way that those which are aligned in the direction of the field can become larger, and those which are not aligned in the direction of the field, they shrink and then they disappear. Okay, so this is the explanation for the BH curve. Now, the interesting thing about ferromagnets is that they can retain their magnetization even in zero external applied field. So that is why they differ from paramagnets. You already saw that some paramagnets actually have substantial magnetic moment, like oxygen, 2.85 Bohr magnetons, but they are not ferromagnetic. And the reason for that is this coupling, this exchange interaction. I've told many times, so by now you understood, but many times it's a source of confusion for people, because they think, hey, this has got high number of Bohr magnetons, what's going on? I don't see it as being magnetic. So what is crucial here is the exchange interactions. So these exchange interactions favor the alignment. Again, as we discussed already, when you have thermal energy, this system has very low entropy, but at higher temperatures you want to go for more entropy, so the spins will become random, and that will happen above the Curie temperature. Okay. So Tc, this Curie temperature, is a measure of this strength. The more the strength, the higher the Tc. So that's what I told you here. Here at low temperatures, the spins are all aligned, but at higher temperatures, the spins are at random, right? The magnetic moments, rather the magnetic moments are at not aligned. So here comes the point I was telling you. If you have a ferromagnet, this is what we just discussed just before the break, then the flux lines, you can see, concentrate within the material. So the flux line which would have gone like this, it actually goes into this. Because the material is ferromagnetic, susceptibility is high. So many examples can be given that the material is ferromagnetic up to this temperature and then become paramagnetic.
Sir, in earlier slide there is a internal exchange interactions
Right.
support magnetic movement to be aligned.
Yes.
Helps magnetic movement to be aligned. But when we apply a field, then the magnetic movements are get aligned. So there is a external exchange interaction between the applied field and the magnetic movements, or
Yes.
between the two magnetic movements there is an interaction.
That's right. So we'll come to that point when we talk about what is a molecular field. What is this exchange interaction? So this exchange interaction we describe in terms of the molecular field. So we'll come to this point when we talk about that.
Generally, suppose we keep two magnets,
Yeah.
so they will tend to flip so that the north pole is by the south pole and south pole.
Yeah, right.
So, but here they are interacting, but how come they always they can have parallel?
No, these are at, okay, so this is an atomic level first of all. And so one atom is sitting here and one atom is sitting here, of course I have not shown. And that atom has a magnetic moment. And this atom has a magnetic moment. But these two atoms, there's a force between the atoms, right? So that force is in such a way that it tends to, in other words, the force is such that the energy of the system is lower when these fields are aligned, when these magnetic moments are aligned. Maybe I'm not understanding. So if you compare the energy of this versus energy where this is flipped the other way, then that would be a higher energy situation. And therefore, for ferromagnetism, but it's not like, it depends on the system. So for example, in antiferromagnet, it is this way and the other one should be the opposite way. So those things depend on the details of the interaction. But right now we are talking about the case where the lower energy is when they align in the same direction. But what I'm trying to say is, it doesn't have to be that that's the lowest energy in all cases. So example is antiferromagnetism, in which the lower energy is when one is pointing one way and the other one is pointing the other way. So really not so good to use that analogy with big bar magnets, because they always behave in the same way. In the big bar magnets, they always like north attracts south and they will always do the same thing. But here you can have different behavior depending on the nature of the forces between the atoms.
So one has to like find out the low energy configuration preferred by the system.
That's correct. So I mean, we'll come to this point later, but since you're asking, I can tell you. So this is the interesting thing, right? Because depending on the distance between the atoms, the atom can behave as a ferromagnetic, or it can behave as antiferromagnetic. Yeah, you will see this. You will see this. It's quite interesting. So it's not like, I don't want to make it like, oh, this has to happen, it's obvious. No, behavior depends on the details. In fact, it depends very sensitively on the distance between these two. Yeah. So you will see that when we talk a little bit later. So here's the interesting thing, is this related to what I told you earlier about fashion. It's like that, you know. So this actually is a spontaneous magnetization by the molecular field. So there's an internal fictitious field which I told you about in paramagnetism case, which in real paramagnets, which tends to make this material spontaneously magnetized. So what happens is that the molecular field tends to, in this case, align the moments. So when those moments are aligned, it makes it easier for the neighboring moments to get aligned. And then neighboring, and then finally it is the whole system has get aligned. So it actually start from a unmagnetized, but by the molecular field, it just keep on getting magnetized and reach this state. So let's talk about that in more detail, but this is the concept. So as I told you, there's a measure of the molecular field, which depends on so this is the molecular field, it depends on the magnetization of the material. So the more magnetized the material, the more the magnetic field, the more the molecular field, which means the more the chances of forming the alignment, right? So that's what I was telling you. Example is like if you have suppose some new company, there are already many cell phone operators. Some new company wants to get market. Then they will say that we will make it, whoever you're calling, top 10 or top 20 people whom you are spending money on calling, maybe local or maybe international, whatever it is, free, if they also on the same service. Correct? Then you may tell them, please, why don't you join this? Then my calls will be free. Then they will assess and maybe they will accept it. Some of them will accept it. Maybe 10% accept it. Those 10% will find it to their advantage if another set of people, their own friends circle, will join this. Correct? So by this effect, you can have a large number of people. So how to increase this effect, right? So initially you must seed a certain large number of people who will be very attracted to this service, and then make it attractive for the interactions, more people to spread. So this is what is happening in this case. So that's the interesting effect.
So, you have value of n. What is gamma here is a constant.
Constant.
So one can calculate h from there, which is a fictitious.
Yeah, molecular field.
There because it's allowed.
Correct.
So what is the order of this h?
Yeah, I will show you some numbers. It's quite interesting actually. The numbers also quite interesting. So now you have the concept. So this is again due to the same Wise who did the domains. He also Curie-Wise law also came up with this internal field. And as I told you, you can get the magnetization in terms of the Langevin function. Okay. So this equation we have seen before. M is equal to A. A is equal to mu into molecular field divided by kT. So we can describe M by M0 in terms of the A factor. Okay. Now we will go quickly through the mathematics. I don't want to spend much time, but it's good to keep the mathematics because later at your leisure you can go through this. So the idea behind this is that we want to explain using this Langevin function, the temperature dependence of magnetization. So now if you see the Langevin function gives m as a function of t as a straight line. Correct? This is coming from the m by m naught, m is equal to kt mu naught by a. Okay. So this molecular field m as a function of t is a straight line. Correct? When applied field is 0, h is equal to hm, so you get m. So now you plot this function which you know m has to satisfy, and you plot the Langevin function. And wherever these two intersect, that is the magnetization. So here is your Langevin function, and here is the straight line which I showed you, which is this, due to the molecular field. So just to repeat, this is the Langevin function which you have seen, I showed you in the earlier lecture, and this is the field which is arising from this graph, okay, which is a straight line, correct, with slope proportional to t. Now where they intersect, here or here or here or here, will give you the magnitude of the magnetization. So the slope is proportional to T. That means at low temperature it will intersect somewhere here, which is a high magnetization. But as you increase the temperature, the slope is increasing, so the line is turning counterclockwise. And because the line is turning counterclockwise, the magnetization is going down. So this explains why magnetization decreases with temperature. Until you reach this point 3. At this point the magnetization is 0. The spontaneous magnetization is 0, which means that is the Curie temperature. Okay? Above this T3, it is paramagnetic. So the point of this thing is to say that using this molecular field, we can explain nicely the temperature dependence of magnetization. Okay. Again, we can go through some arithmetic, okay, and we can find that ms by m0, that is the saturation magnetization, is determined only by T by Tc. That means, in other words, according to this model of the molecular field, all ferromagnets have the same ms by m0 for the same T by Tc. So what this means is, if you know the T by, if you know for a particular temperature, you know the Tc of nickel, and you know the M0 and Ms of nickel, even for iron, it will have the same Ms by M0. So you can use that to predict the magnetic properties of ferromagnets, which are difficult to measure, by using this law of corresponding states. So the prediction is that this will yield the similar values of the Ms by M0 for the same T by Tc. Now we can go through some, I should say, minor points, because these this is because normally we calculate atoms per volume, but volume varies with temperature. So in principle we should not use volume, we should use mass, because mass is fixed, right? So we can change from to a quantity which is dependent on the mass of the material rather than the volume of the material. But don't worry about that, that's a kind of a not a so crucial matter. So we can express everything in terms of this sigma, which is fixed rather than quantity which depends upon the volume. Okay, so if we do that in terms of the sigma, also we get the same logic. So it's really not that important whether you use this or that from this point of view, from the point of view of concepts. Now you remember that in the case of paramagnet we had the Curie law, that susceptibility is equal to C by T. I just covered yesterday, right? So if you want to include the materials, I think somebody else also asked me this. I think you asked me from para to ferro, then you can make such a relationship. Chi is equal to C into T minus Tc. Right? You can modify this relationship, which is the Curie law. You remember that is T minus theta to T plus theta. Correct. So here you can take this value and then include this for the ferromagnets. So let us think about what we have covered so far. The idea behind ferromagnetism is that there's an internal molecular field which we will calculate its magnitude, and those internal molecular field creates an alignment of the atoms, magnetic moments of the atoms in the parallel direction. Right? This is the concept which we use. So, however, that effect decreases with temperature as we demonstrated. Finally, you come to the Curie temperature. As I told you, we can plot the values of magnetization as a function of grams, so it's a fixed quantity, versus temperature. Now we want usually as high Tc as we can. So you can see cobalt has a higher Curie temperature compared to iron. Again, so there is no perfect material. Iron, the saturation magnetization is higher, but the Tc is lower. Nickel, both are not so good compared to iron and cobalt. Okay. In addition to these Curie temperature, as I told you, the material can behave differently depending upon the mechanical properties and also whether there is a phase change or not. I think you asked, shape memory alloys are basically crystal structure changes. So if you see, in the case of iron, for example, the Curie temperature is in the BCC regime. It doesn't get a chance to go up to the FCC crystal structure. In the case of cobalt, the material is magnetic in the HCP crystal structure. It is also magnetic in the FCC crystal structure because the TC is over here. The FCC HCP transformation is over here.
So what the R indicating?
R is recrystallization. I'll come to that. Then in the case of nickel, there is no phase transformation in the crystal structure. So TC is somewhere here. Now, the recrystallization temperature is the temperature at which after you deform a material, it will spontaneously form new strain-free grains. So again, you can see in the three cases that in one case, the recrystallization temperature is below the TC. In one case, it is almost equal to the TC. In another case, it is above the TC. So you can understand the relationship between mechanical properties, which is what recrystallization measures, and the magnetic properties. So in some cases, for example, this case, the material, you can make it recrystallize, but it is already paramagnetic at this state, which means, what is the purpose of recrystallization? The purpose of recrystallization is to reduce the defect density by forming new grains. So in this case, you can reduce the defect density in the soft magnetic material by recrystallization because it's still ferromagnetic. But in nickel, by the time you recrystallize, it is already not magnetic.
New grains are
Formed, which don't have the defects which are there in the deformed structure. So this gives some clue about processing. Okay.
How do defects affect magnetic properties?
Yeah, so the defects essentially, they can affect the domain wall motion, they can affect domain wall nucleation. So domains can nucleate, not domain nucleation and domain wall motion. Yeah, mostly they do this. In the case of magnetization, as we just discussed in the beginning of the lectures, we discussed whether which is better. Is it better to use classical, which is easy, in which case we have the Langevin function, or we should use the Brillouin function, which is to do with the quantum theory. So let us see, based on our experimental values. So if you plot this saturation magnetization as a function of T by Tc, why we plot like this? I told you, it's based on the corresponding states which I just introduced few minutes ago. So if you plot sigma s by sigma naught as a function of T by Tc, then for different materials they should fall on the same curve according to this molecular field hypothesis, right? It's normalizing. So we normalize this and then we plot it. Now the question is, the classical value is not very good fit for this experimental curve. So if you have J equal to 1, we'll just wait. It's okay. We'll just wait now. Now we'll wait. Okay, so if you have J equal to 1, it's not bad, but it's not perfect also. But you can see J equal to half matches quite nicely with the experimental values. That's why in the previous lecture I was emphasizing J equal to half, because I know that it's going to come up in this case. Okay, so what this means is, it is definitely better to use the quantum theory in the case of ferromagnetism, because although this is, it's not completely off, right? It's not terrible, but it's not that good either. So you can see that the quantum theory fits better with the experimental data. Okay, so now in the case of ferromagnetism, what are we looking at? So we need the quantum theory, which means that the magnetic moments are not all over the place, they are quantized. So at T equal to 0, maybe at T equal to 0 they are perfectly aligned, but as you increase the temperature, the entropy increases. So the magnetic moments, some of them will be here, but some of the magnetic moments of the atoms will be here and here. Then as you go close to the Curie temperature, they can be wider and wider in more and more entropy. And finally, in the case of the paramagnetic, they can be all over the place. So this is a schematic representation to show you how the temperature plays a role in affecting the magnetic properties. Now, if you plot the susceptibility, as you know, the 1 by susceptibility will increase in a straight line because C susceptibility is equal to C by T. So if you plot 1 by susceptibility, it will be linearly proportional to temperature, correct? So that this is the behavior you will see, and you can identify where is the Curie temperature. So the Curie temperature will be here where the ferromagnetism and the paramagnetism meet. There are some details. I don't want to spend time on this because I want to move forward to the other parts of the course. So now comes the point which was just asked. I knew I'm going to answer, so I waited till I waited till this slide. So what is the magnitude of this molecular field? Okay. So we can calculate the molecular field. Of course, we need to do a lot of assumptions and so on and so forth. But the net result of all this is that the molecular field are much larger than the applied field. That means the internal field is much larger than the external field. That's why it is spontaneously magnetized. Internally itself, there's a strong drive towards the spontaneous magnetization. And the other point I've told many times is that the mu h in ferromagnets is almost similar to that in the paramagnetic substance. See, in fact, the mu is only 2.22 Bohr magnetons, less than oxygen, correct? But in fact, that means ferromagnetism is due to the alignment of spins, not because the magnetic moment of the atom itself is very big. It's a very common misconception. So, in putting in a qualitative way, even the small magnetic moments, by working together, they can create a giant effect. I've been telling this throughout the course. Even if you have large moment atom, but they don't work together, the effect is small. Okay, so the molecular fields, when you calculate, turn out to be much larger than the applied field for iron. So what is this molecular field? What is this exchange field, right? Of course, it's a way to calculate. It's a model. So one can calculate the molecular field in terms of the exchange forces. And this is basically purely quantum mechanical. There's no classical way to calculate this. So essentially the exchange forces are some J exchange multiplied by the spins on the two atoms, so if there are atoms I and J and they have spin angular momentum Si and Sj, then we can calculate the exchange interaction. Now comes the point you were asking, and this is why I say I don't want to give that analogy of bar magnet, because if J exchange is positive, then the material is ferromagnetic. But if the J exchange is negative, you can get antiferromagnetic behavior. So the same atom placed at different distances, so to speak, can behave differently. Or different atoms, because they have different lattice spacing, you will see, will behave differently. So distance becomes a very important factor. When the 3D electrons are very close, then the J exchange can be negative, then you will get antiferromagnetism. Okay, so what does this mean? So the whole thing which I just told you was already done by these two scientists, Bethe-Slater. And what does it show? It shows that you have an exchange integral, J exchange. If you plot this as a function of distance, so this is the atomic, this is a ratio, this is normalized of the atom, radius of the atom divided by the radius of the 3D electrons, right? So if you plot this, you will see that the exchange integral varies in this way with distance. So J exchange can be positive, J exchange can be 0, and J exchange can be negative. And because this is J exchange is positive, 0 or negative, then nickel is on the positive side, cobalt is on the positive side, iron is on the positive side. So its J exchange is positive. So it is ferromagnetic.
This x-axis,
Ra by Rd. Ra divided by R of the 3D electrons.
so 3D has a band structure here.
Yeah, you have to take. This is just a classical. Yeah, so that's like a.
The reason we are not getting mu s equal to 5 mu b is because of this band structure.
Yeah, that I come to.
Because of exchange.
I come to that point. That's a little bit later. I'll talk about this. Yeah. So the point is that the exchange integral can be positive, 0 or negative, and if you see the systems, manganese, if you plot its value, will be falling in this category. So that means we predict that manganese will be antiferromagnetic, which is actually correct. So one way to tune the magnetic properties in these type of materials is by tuning the distance between the atoms, and that can change the magnetic properties. So by changing the crystal structure, for example, you're changing the spacing, you can change the magnetic property.
So at very high pressure iron can become.
Oh yeah, there's a lot of interesting pressure effects on magnetism. Very interesting, sure. You can change the properties very easily. I mean, this is, of course, as you were saying, it's just a approximation or a lot of assumptions go into this, but still quite useful.
So experimentally this can be this ratio can be used.
This you can ratio doesn't have that much meaning because some of the electrons are actually in a metal are free to go, but we can make certain simple models because you have to start somewhere. So that explains why Bethe-Slater curve explains why manganese bismuth is ferromagnetic. So for example, manganese is antiferromagnetic, but by adding bismuth you can shift this value to somewhere here. So you can make it ferromagnetic. You see how useful that is. So So this concept is very powerful to change the magnetic properties. So you can change the exchange integral by alloying basically. Same concept for Heusler alloys. Same concept. Distance is very important, and you can use the Heusler alloys you can have a wide range of magnetic properties by tuning the interatomic spacing. Okay. So what is this exchange integral? You can represent it in terms of some quantum quantities. I don't want to talk so much about that because we want to move on to the other factors like antiferro and ferromagnetism. So anyway, now comes the point I already told you, I promised to tell you. I said you can actually, of course, the system is not that of individual atoms with individual electrons only paired to that atom, but in fact it is a band, right? So in metals actually we will have elements, not really, the electrons are in a sea of electrons basically. So what you have in reality is some splitting of the electron energy levels as you come closer and closer. As the atoms come closer and closer, due to Pauli exclusion principle, they cannot occupy the same quantum state. So it has to split, it has to broaden. So it broadens and it forms these kind of structures, right? So 1s will broaden here, 2s, 2p. But for us, main interest is in this. So you can see that 4s goes below 3d because of the broadening. So first 4s is filled up, then 3d, and so on and so forth. So the splitting occurs due to the Pauli exclusion principle, and the extent of splitting, that is the width of this, depends on the level. So actually one can do, as I said, very sophisticated calculations. One can do these type of calculation and find out how the electrons are arranged for, say, nickel. One can calculate how the electrons are filled. One can calculate this filling, and from this filling we can find out how many unpaired electrons there are. And these unpaired spins are the ones that can contribute to your magnetic behavior. Okay, of course this is a lot of computation and so on and so forth. So let us, before we move forward, let us just maybe summarize what we have understood. So basically there's a molecular field, internal field, that is one way of describing from the old days, right, from paramagnetism, which says that those align. But if you look from quantum perspective, basically there are spins, and those spins, there's an energy associated with the interaction of those, which we describe by means of an exchange integral. So if that exchange integral is positive, then the energy is lowered by the spins being in the same direction, which means that you have ferromagnetism. If the exchange integral is negative, then it favors the anti-parallel state, which is anti-ferromagnetic. But this behavior can be tuned by changing the composition so that the distances can be changed. So alloy can behave differently from a pure metal. See, bismuth itself is not magnetic, but by adding bismuth, it's kind of interesting, right? Because manganese is anti-ferromagnetic, but by adding some non-magnetic material, semi-metal, you can make the anti-ferromagnetic material into a ferromagnetic material. Definitely also can be done by pressure. It expands the lattice, which is what you expect, correct? So it expands the lattice and that shifts it to this side and makes the material positive. Okay, I think it's 12:20. Maybe we stop at this stage.